All right, so today we're going to go through what's known as the Hilbert transform, and you'll see some examples of how it's implemented. We won't really discuss the analytical ways it's applied. We're just going to look at how it's applied to data, and then we're going to look at what is known as mirroring in the context of signal processing. All right, so the Hilbert transform is named after the famous mathematician David Hilbert. He's got his hands in almost everything in modern math at least. In this equation, we're going to write it as ht, and it's a transformation and applied to some signal x at t, and it's equal to 1 over pi pv, the integral from minus infinity to infinity of x of tau divided by t minus tau d tau, where this PV stands for the Cauchy principal value, and you won't need to be able to solve these types of integrals. We're just going to do it using a discrete Hilbert transform, and we're just going to apply it directly to data. But usually this integral pops up when you're studying complex variable theory. Okay, so physically the Hilbert transform acts as a linear filter, and specifically it shifts the phase of the signal by pi over 2 without changing its amplitude. And as a result, if our signal x of t is real, then so is its Hilbert transform. And if we were shifting by pi over 2, so if we apply twice, we're going to end up with the same signal but opposite sign in this case. So if we compute the Hilbert transform, which we wrote as ht, Hilbert transform of the Hilbert transform. And actually, let's reduce that notation. Let's switch to h. So if we apply h to h, which is applied to x of t, this will be equal to minus x of t. So it's equivalent of just flipping the sign. And then if you apply the Hilbert transform 4 times, then you just get back the original signal. Okay, in our use of the Hilbert transform, we're going to be using it to construct what are known as analytic functions. That's really kind of the main benefit of the Hilbert transform in this context. Okay, so first let's say you can use it to construct signals that you can then decompose into a polar representation. So just like we did with the complex amplitudes when we applied the method of multiple scales, and we broke that into an amplitude times an exponential to some phase, we can do that to a signal using the Hilbert transform. And specifically, in this case, we're going to think of what's known as an analytic signal. And an analytic signal is simply a complex signal that has an imaginary part, which is the Hilbert transform of the real part. And so, for example, the analytic signal, which we're going to represent using a little dagger symbol, so z dagger of t is defined as z dagger of t is equal to z of t. So that's our real signal. So that's what you would get from like a measurement, plus j times the Hilbert transform of z of t. And that is our analytic signal. The real benefit of this is that after we construct this analytical signal, we can then expand it into a polar form such that z dagger of t is equal to some amplitude a of t times e to the j theta of t. So we can do this polar representation of the signal itself, where we have some instantaneous amplitude and some instantaneous phase. And then we can then go and compute an instantaneous frequency, which we'll just say is omega of t. That's simply d theta dt, just simply the time derivative of the phase. Okay, so in practice, the discrete Hilbert transform has to be applied to discrete signals, just like we apply to discrete Fourier transform to discrete signals. We're not going to go into the algorithms that compute this, but most of them are rely on Fourier transforms, specifically FFTs and IFFTs, and doing so actually ends up introducing high-frequency noise or oscillations into the output, meaning that in our instantaneous amplitude and instantaneous phase, you're going to end up finding these high-frequency oscillations, and we end up having to apply low-pass filtering to that. We're going to talk more about filtering probably Thursday and just what it is in general. For right now, we are just going to apply a very aggressive low-pass filter to remove all of those oscillations. Okay, so one thing I did not mention is that the Hilbert transform really only works for monochromatic signals, which means a signal that only has one frequency in it. So in your homework, you're dealing with just a Duffing oscillator. And the reason is because you can't apply Hilbert transform. You can, but you're not going to get a good result out of that, a useful result to a signal that has multiple frequencies in it, or like a multi-degree of freedom system. And that's why you're only looking at a Duffing oscillator. When we go and do signal decomposition, this will then allow us to decompose the signal into a set of signals that each have only one frequency, and then we can apply Hilbert transforms and so forth. And then we can use that to then interrogate the signal if there's internal resonance and so forth. That's where we're going. Okay, so for now, I just want to tell you that this modal class includes a function called instant amp freq that you can use to compute an instantaneous frequency, amplitude, phase, and frequency. It employs this Hilbert transform, and it applies it applies a low-pass filter based on a Butterworth filter here. And the examples I'm going to go through here will use that function, basically. Was there a question, Mohammed?
About the Duffing oscillator, you said the Hilbert is just going to work with signals that have one frequency.
Yeah.
And I was confused because the Duffing oscillator, we have only one frequency.
We'll come back to that. We'll come back to your question after this. Okay. Okay, so it's a very good question. We'll get to that. All right, so here we're going to consider just a first example of just a signal that I've created, which actually has two frequencies in it, but these frequencies are very close together. So in this case, the signal is x of t, which is equal to e to the minus 0.025 times t. That's our exponential decay here. And times the sine of 2 pi times f1 t minus the sine of 2 pi f2 t, and plus some phase phi. And here, although there are two frequencies in this signal, they are extremely close to the point that in this kind of application, the Hilbert transform sees that it is a single frequency.
Just to confirm that this sign is not in the exponent, right?
No, none of this is in the exponent. Here, let me pull that down. Yeah, the exponent of the e to the minus 0.025 t, that is the amplitude of this signal. Okay. And so we're going to simulate this or compute this signal from for a time of 0 to 200 with a sampling rate of 100. We're then going to plot the signal and its corresponding wavelet transform. We'll then use the Hilbert transform to construct the corresponding analytic signal. And we'll plot that in 3D. And then we'll compute the instantaneous amplitude and frequency, and we'll plot those. And then we're going to superimpose the amplitude and frequency onto the time series and the wavelet transform, respectively. Okay, so just looking at A here, this is what the signal looks like. It increases amplitude and then decreases until it actually hits near zero around a time of like 95, and then it increases a bit, and then finally decays to zero around 190 or so. So this goes through what we would consider to be a beat in that case. Beats arise when you have frequencies that are closely spaced. In this case, these two frequencies, as F1 and F2, are extremely close together. That gives rise to this beat that we see here. You should be able to see it in the wavelet transform as well, how there's this very dark beat in the very beginning, and then it goes to almost zero amplitude, and then it increases again. So just taking a look at this analytic signal, you can see when it's plotted in 3 dimensions, both the complex plane as well as expanding that in through time. You can see you get a very nice spirally, very clean signal in this case. And if you look at the red and then the blue, you'll see that they are very much the same. If you were to zoom in, you'd find that they actually just have opposite signs due to that Hilbert transform. Sorry, they don't have opposite signs. They're phase shifted by pi over 2. That's what it looks like, because that's what applying Hilbert transform 1 does. Okay. You can just directly compute the instantaneous amplitude and the instantaneous frequency. That code that I'm using, which is shown right here, that function just does that for you. Applies Hilbert transform, computes these quantities. And you can then plot them as function of time. And then on the right, I've plotted them on top of the time series and the wavelet transform. You can see here how the Hilbert transform captures that amplitude of the signal as well as the instantaneous frequency. Now, when a component or when a signal dies out and basically goes to zero amplitude, the instantaneous frequency will drop down to 0. And so when you see this little dip here, that's because the amplitude becomes near 0 and the frequency wants to just disappear. And that's what happens over here, is just that the amplitude goes to 0 and the frequency is no longer aligned with this response. Okay. All right, so in example 9, we are just going to apply this Hilbert transform to the Duffing oscillator response that we saw in example 3. We're going to study the effect of this cutoff frequency of a low-pass filter. So we're going to talk about this more on Thursday, but for every filter you have what's known as a cutoff frequency. For a low-pass filter, that means that you're going to try and get rid of everything above that cutoff frequency. And you're going to keep everything below the cutoff frequency, hence low pass. We're going to study the effect of that, and we're going to see some of these oscillations that I've been talking about, and then we're going to apply this. We're going to choose the right cutoff frequency and then just plot the instantaneous amplitude and instantaneous frequency on top of the time response and the wavelet spectrum. Okay, so in that example that we looked at last week, there were 2 different initial velocities considered, a low and a high initial velocity. That's what I'm showing here on the left and the right. And for the cutoff frequency, we started off with a frequency of 1 and then decreased it by 10 all the way up until we got to 1/10,000th. So the red and the black are basically on top of each other in this plot. I'm going to zoom in here so you can see better. You can see here that, at least in that red one, we have oscillations occurring at a much higher frequency than what the amplitude is actually doing. And if we scroll down a little bit and actually look at the signal, you can see that there's actually no oscillations in the true amplitude of that signal. So this is what I'm talking about when I say that this discrete Hilbert transform introduces high-frequency oscillations that need to be filtered out. Okay, so it also turns out that if you over-filter or you define a cutoff frequency that's too small, you end up cutting out content. In this case, this is what that green signal looks like. On this plot, the blue, it's not necessarily like a right or a correct cutoff frequency, but there's more like a range that you're thinking of. There's no like exact answer of what you should use. but certainly if you use the red one, you're going to get something that doesn't match the actual signal. If you use the green one, that's also not going to match the actual signal.
Is there some sort of like convergence that you can use to
Yeah,
know what the right one is?
I mean, yeah, you absolutely could define a convergence based on like the peak value. I mean, we're not going to do this, but maybe I'll go and modify the code to do that. It's not a bad idea, actually. Because you could, if we come here and we take a look at this, you can pick the peaks, and then your instantaneous amplitude should intersect that with minimal oscillations. And so that's, the derivative should be relatively smooth. There's definitely a way to do that. The code does not have anything like that. You just got to play with it until I come and implement something better. Okay, so for instantaneous frequency, at this relatively low initial velocity, the frequency is pretty much constant. And so you can see here clearly these oscillations in the red and the black, and in the green one we have way over filtered and it's way overshooting that response. You'll see a similar thing for that higher amplitude. You'll see these oscillations, although their kind of mean value tracks what we're looking for, and then when we overfilter, it deviates from that substantially. Okay, we'll just take a look briefly at what they look like superimposed on the time series and the wavelet transform, and you can just see how the instantaneous amplitude tracks the amplitude of the signal, and the instantaneous frequency tracks the band in the wavelet transform. So usually what I do, if I'm trying to figure out what the filter should be, is I'm plotting these bottom two plots in B, and I'm looking at what it looks like. I'm checking particularly that instantaneous frequency, because if the instantaneous frequency is something like, then I know I haven't filtered enough. And if it's something like, then I know I've overfiltered because it's not lining up with what's in the signal itself. Yeah, that's usually what I do.
So we don't really need to chase zeros, just get it to look like the wavelet transform.
Yeah. Yeah. This is a good enough kind of thing, and good enough works just fine for this kind of analysis. It works. Any other questions? Okay. In that case, we're going to talk briefly about mirroring, because mirroring appears in several of the codes that we have been using and will use, and I just want you to have an idea of what it is exactly in general. So usually, or not necessarily usually, but it's quite common for numerical artifacts or errors to be introduced when we're doing a time frequency analysis or signal decomposition, as we'll see on Thursday and next week. This often happens just due to the processing of the signal, and they particularly will show up at the beginning and at the end of a signal as well, which we then call end effects, effectively. So if we're thinking of like a transient vibration response of some nonlinear system, all of the strong nonlinear behaviors can happen at the very beginning of the signal when the energy is the highest. At the end of the signal, if we measure for long enough or simulate long enough, we should have like a zero amplitude, so we don't really care what happens there. But at the very beginning of a signal, we do care about what happens, because that's where all this interesting behavior happens. So if we're doing any kind of the signal processing, and that is messing up the content at the beginning of the signal, that is going to mess up our interpretation of that nonlinear behavior. So in order for us to overcome this issue, we're going to apply what's known as mirror imaging. And basically, we're going to extend the beginning and in this case, the end of the signal as well. We don't really lose anything by mirroring the end of the signal, so we're going to do it anyway. We're going to extend the signal by mirroring such that all of those numerical artifacts end up being captured into the mirrored portion, which will then just cut off of the signal and have a clean signal in the beginning and end still. Okay. Yeah. All right, so we're going to consider a time series X. This is just a discrete signal or a continuous signal, doesn't really matter. And we're going to then mirror it or produce the mirrored signal as, we'll say, x sub mirror of t is equal to composition of x mi of t, and that will be the mirrored portion at the beginning of the signal, x of t, and then x sub mf of t, and that's the mirrored portion at the end of the signal. And that will be transposed. And then here, t now lives on the domain of minus ta to tf plus tb. So by doing this mirroring, we are extending the signal in both directions. And so TA here is the duration at the beginning of the signal, and TB is the extended duration at the end. Okay, so a rule of thumb for mirroring is that our mirror image must preserve smoothness in the instantaneous frequency at the symmetry points. That means at the points where we have this mirroring occurring. And so that the expanded signal is continuously differentiable at those symmetry points. And so what that means is that we require that X mirror, a mirror image or mirrored signal, this needs to be at least differentiable once continuously, and true for t at 0 minus, 0 plus. So that's the symmetry point at the beginning of the signal, as well as for t in the range of tf minus and tf plus. And that's the symmetry point at the end of the signal. I believe this sentence a little bit weird, but it kind of gets the message point part across. So generally the most convenient type of symmetry is to use an even expansion whenever the velocity at a symmetry point is equal to 0 effectively, so you'll have some maximum displacement value. In that case, you will do this even expansion, which we'll see on the next page. Otherwise, we're going to do an odd expansion. So in this case, what we're looking at is that our x mi, that is the mirrored portion in the beginning of t, this is going to be equal to x of minus t for t within 0 to ta. So basically, we are going to take the portion of the signal from 0 to ta, and we are going to flip that using even symmetry and put that in our mirrored image signal. And on the next page, you'll see some pictures of what this looks like. And generally, you want to do this when the velocity is 0. However, in practice, you typically do this for a very small velocity. In the codes that you guys have, this even expansion is just the default value. And if you're unhappy with those, what comes out of that, then you can switch to an odd one. Okay, and we'll see on the next page kind of what happens when you use the wrong type of mirroring. Okay, in the case that velocity is not 0, in that case we're going to use an odd expansion, in which case we'll say xmi of t is equal to minus x minus t for t in the range of 0 to ta. And here I've only done this for the beginning, but this is also true for the end of the signal as well. All right, let's take a look at some examples here. So this example here, this signal is x of t is equal to the sine of 6 pi t. And here we're looking at just the beginning, mirroring at the beginning of a signal. Okay, so top plot we have the time series. Bottom plot we have our wavelet. We have the signal with the mirror extension. This portion here, this is xmi of t, and then from here on, this is x of t. And then to the right is a close-up of that. So this is a case where odd mirroring has been used. You can see that at t equals 0, which is the point right here, we have a 0 displacement, in which case we're going to want to extend this using an odd mirroring. If we were to use an even mirroring, what we would get is some kind of spike like that. So there'd be a very sharp inflection point at t equals 0, and that's what we're trying to avoid. Okay, so beneath that are the wavelet transform for this X mirror signal, where the wavelet transform has been computed on X mirror, and then the mirrored portion has just been chopped off in the wavelet transform. And you can see that there are no end effects at the beginning of time. However, there's still end effects at the end of the time, so we still have these end effects here. Also there as well. On the right is the wavelet transform, just the original signal, and you can see that we get these end effects both in the beginning and at the end of the signal. So the mirroring gets rid of these effects effectively. That's the whole idea.
Where are those end effects coming from, though?
It comes so okay. All of the transforms that we're using are defined over from minus infinity to infinity. But we don't have an infinite signal. We don't have a signal that stretches to infinity. We have some truncated signal, and that's what causes these kinds of effects. And then also things like, is the signal periodic within the window that we're checking? These are the kinds of things that occur that cause these effects. For the wavelet transform, yeah, it was exactly what I said, same thing. So it's all due to the discreteness and the truncation of not using an infinite signal. And similar things arise in Fourier analysis as well. We're just not going to study that here.
Would I learn about this in like a discrete mathematics book, or?
Probably not. I mean, we're at the point where we are going through research that's like 10 years old. Maybe like 15 years old. So maybe in like 20 years. I don't know. I don't know how long it takes, but
That's what I love about this class.
we're not at this point. We are departed. So when we did like multiple scales, that was a very established method that's been around for like 50 years, and there are textbooks on that. Then we went and did CXA, and there's no real textbook on that, although that's like 25, 30 years old. And when we did nonlinear normal modes, that's still like an open field of research. And now we've just, all the data-driven stuff except for Fourier transforms and basic wavelet transforms, that's, established. But now we're looking at things that are like actual like research topics that are within the 2000s, since like 2000s. And so when we do signal decomposition, we'll look at like proper orthogonal decomposition, which has been around for like 70 years. It's very well established, used throughout many different fields. And then we'll move towards things that are active research topics or recent research topics as well. So to answer your question shortly, there's not, to my knowledge, it's not really a textbook that addresses this stuff yet. Okay, here is another signal. In this case, this is x of t is equal to the cosine of 6 pi t. And beneath this, in the middle, you can see what an odd expansion looks like and what an even expansion looks like for this particular signal. So in this case, at t equals 0, the signal starts at the value of 1, actually. And we know that cosine is actually an even function, so you should expect to use an even expansion here. In this case, if we use an odd expansion, what you end up with is additional numerical artifacts at the beginning there that are even worse than what you have at the end. And if you use this even mirroring, what you get is these no numerical artifacts there as well. So you can think of this in the sense that if you are studying a signal that has, if it's a displacement response and you're giving the system an initial displacement as its starting condition for a transient response, in that case, you would want to use an even expansion. If you had a 0 initial displacement but some non-zero initial velocity, then you would go ahead and use an odd expansion as well. And generally, when I do this, I just start with even. It's usually what I start with. And that's why that's the default in all of the codes. And if it's not working or looks, if it looks like this figure right here, then I switch to odd. And you also have the option of not using mirroring. And in any of the codes that I have given you, you'll, instead of putting like so for in the codes, so if you supply E, this gives even mirroring. If you supply, that's an O, a lowercase o, this gives you odd mirroring. And if you provide anything other than those two, and still provide a value, I mean, if you don't provide anything, it goes to even. But if you give it anything else, it will do no mirroring, which sometimes works better than mirroring. I don't really have a rule of thumb of when that happens.